All right, so I'll at the end of class hand the exams back. But overall, it's the average is kind of about where I expect the second exam usually to be. I think the median was like 67, 68. But the kind of average grade in the class right now puts it right at a 79 for the median, and I think like a 76, 75 for the mean. There might be one unofficial drop in there that's pulling the mean down a little bit, but so overall, I'm pretty, it's usually where I kind of see grades at going into the final. If you didn't do as well as you want on that exam or the first exam, remember kind of the weighting changes. Your best exam gets weighted the most. So the way I have it currently showing up on Canvas, I think is showing it as though it's your best two exams. So if you didn't do too well on them, it's kind of worst case scenario. If you do better on the final, you could change your grade quite a bit. Because I think the worst exams, let me see if I can remember this. I think it goes 25, 20, and then down to 10. Right. So if you replace a bad exam with a better exam in the final, you really kind of influence those weights. Okay. I also will hopefully by Wednesday have those Excels graded, the last Excel assignments. And I'll kind of get those factored into your grade as well. You'll also probably see me put up the next Connect assignment, just so you can kind of start chipping away at that as we kind of start covering material. Today we're kind of talk about what we did with hypothesis testing, because we're going to keep doing hypothesis testing, but we're going to do it in a different aspect. So I want to make sure we have a pretty good understanding of what we're doing before we move on. So we'll kind of be doing a review today, but kind of showing you some new stuff as well. Okay. Any questions for me? Yeah.
With the finals, is that going to be over just the new material?
Just from what we cover from here to the end. Yep. But like I said, we will be doing some more hypothesis testing stuff, so that'll be part of it. But I'm not going to go back to asking you about things that we did in week 2. I mean, I guess all this is kind of cumulative in a sense, but any other questions? All right, so what we were doing with hypothesis testing was we didn't know where this true population parameter laid. And we have these 3 different types of examples. We had sample means, so we knew the population variance, sample means, when we look at a sample variance, and then we look at sample proportions. Okay. But the general idea, I'll just kind of use the sample mean to get at this, was that we've got some assumed true, I don't know, we'll put a number to this, assumed true population mean. We then take a sample, and our sample mean is inconsistent with that. Okay. Now, it depends if we have a right, left, or two-tailed test. For the sake of this example, let's assume that we've got a right-tailed test. So that our p-value was going to be the probability that we saw this as our sample mean if what we assumed to be true was in fact true, or anything even more inconsistent with that null, or that assumed true value. So how did we find that probability? Well, it depends if we had a known population variance, or we were dealing with a proportion example. We said we get to use that standard norm or the z-table. Once I turn that sample mean into what we call a z-statistic or a test statistic, I can look that up in the table. The table would give me the area to the left. If I don't have the area to the right, just 1 minus that. So that's what we were doing when we did the p-value approach. Just hopefully looking a little bit familiar. So we'll assume that we have a right-tailed test for now. And we're going to talk about something called critical values. Okay? So I'll give you a conceptual idea of what they are, and then we'll work through a couple examples. We'll kind of see how the p-value approach compares to what we call the critical value approach. So when I looked up that test statistic and found that corresponding p-value, we said we would reject the null if the p-value is less than this threshold alpha we set. We said, look, we're okay making errors this proportion of the time. So if the probability of what we saw falls below this threshold, we're okay rejecting that null hypothesis, because it's gotten so unlikely, that probability has gotten so small that it's likely what we assume to be true isn't in fact true, and the actual distribution, right, is shifted somewhere over closer to what we saw from our sampling. So there's this threshold alpha, and if our p-value is less than that, then we can reject. Well, if we think about that visually, my p-value represents a probability or the area under the curve to the right of my test statistic. Well, I can think about if alpha was larger than my p-value, let's say, I don't know, we'll put some numbers to it. Let's say the p-value is 0.03, and here my alpha is 0.05, right? Well, then I know that there's going to be a certain number of standard deviations away that corresponds to that probability of 0.05, right? And because my p-value is smaller than 0.05, right? My p-value is 0.03 here, just for the sake of this example. Then whatever that number of standard deviations away is, my test statistic represents that I found sample evidence a further number of standard deviations away from that assumed true value. So we're going to set not a threshold for alpha, or we're not going to be comparing kind of the area and the tails here, but instead we're going to use alpha, oops, use this color, to find what we're going to call a critical value. All the critical value is essentially now not a threshold probability, but a threshold number of standard deviations away. So now if I ever see a test statistic, and I'll say more extreme here because in a second when we deal with like a left-tailed test, everything's negative. So like the sign would have to switch because larger negative values are actually less. So we're just thinking about the magnitude here. Anytime that critical value, that cutoff value that corresponds to this alpha threshold I set, if that's less than the value of my test statistic or how many standard deviations away my sample evidence was, then I'm okay rejecting. So with the critical value approach, as opposed to just comparing the p-value to alpha, and that told us if that's true, we rejected. Well, now if my test statistic falls in this rejection region, and this is why the critical value approach is kind of nice because it has a nice visual to it. Once I plot that threshold number of standard deviations, I draw an arrow kind of going into my tail. If my sample evidence or my test statistic falls anywhere in that region, I reject. If it doesn't, I fail to reject. So another way of thinking about this is, if the absolute value of my critical value is less than the absolute value of my test statistic, then I'm okay rejecting. Well, why do I take the absolute value? Well, for a right-tailed test, it doesn't matter, right? They're already positive. But for a left-tailed test, everything's going to be negative, and so I actually need to kind of just look at the absolute value. What's larger in magnitude? If that test statistic is larger in magnitude than this critical value, you're okay rejecting. Think about this way, the critical value is saying, look, if I see sample evidence that's more than 2 standard deviations away from this, then I'm okay rejecting. It was so many standard deviations away that this probably isn't the true mean. Okay, so that's kind of what we're doing with that critical value approach. And they're always going to lead to the same decision, right? Think about it this way. If my p-value, the only way my p-value is less than alpha is if my test statistic is greater than my critical value. So it's almost like just kind of comparing, if I had like all these x values and a function that calculated y, it's just like instead of comparing the x values, I'm comparing the y values, right? So instead of comparing the areas in the tail like we were before, now we're comparing the x-axis values. And I say x-axis, right? I guess we could call it z-axis because we're looking at the z values, but kind of our kind of more traditional x-axis, we just refer to that as the horizontal. Right? So what does this look like? We'll go through a couple problems here. So we'll do some proportion ones, just for proportion one, just to get a little bit different of a look at this. But remember, our test statistic for proportion was a little bit different, right? In our denominator, the thing that represented the standard deviation of our sample statistic, we instead of kind of having this known population variance or being able to calculate a sample variance, we knew it followed this, right? So now the steps, instead of we're doing the critical value approach, figure out your null alternative, what type of tail test you have. You need to know what alpha is. Using alpha and the type of test, you figure out your critical value. You then calculate your test statistic, compare the test statistic to the critical value to make your rejection decision. So the steps are similar to the p-value approach, but just a little bit different. So I've kind of already given you a little bit of an idea of what these critical values and these rejection regions look like. but I'll kind of show you how you find it here. So let's say I instead had a left tail test. Right? Well, there, only evidence on the left-hand side would go against the null. So there I'm looking for what's the critical value that gives me alpha in this lower left tail. If my z value is, or my z value, my standard normal or my z table is centered at 0, then when I'm looking at a left tail test, my critical values should all be, negative. If I'm looking at a right tail test, all my critical values should be positive. So they're going to be the same value since this is a symmetric distribution. But for a left tail test, I'm going to have all of alpha in that left tail, so my critical value will be negative. Right tail test, all of that alpha is in the right tail, so I'm going to have the same value of positive. Okay? Now, for the right tail test, like I said, once you find that critical value, you draw your arrow to the right. Well, for a left tail test, you draw your arrow to the left to kind of visually represent that rejection region. And if my test statistic falls anywhere in this region, I'm okay rejecting. If it doesn't, I fail to reject.
So if it falls to the right of the critical value.
So in this case, for a left tail test, let's say my test statistic, I don't know, what's some values to this that we'll look at in a second. So let's say it's 1.96. I don't know, this is 1.7 is my test statistic or my z statistic. I'm just plotting that. It doesn't, sorry, these should all be negative. It doesn't quite fall in my rejection region, right? So I would say I fail to reject there. And that follows the rule I had over there, right? Because remember, I'm comparing the absolute value of these. So the absolute value of my test statistic is actually not greater than the absolute value of my critical value, right? 1.7 is a little bit lower than 1.96. So I can't reject. Right? The only way I can reject is if this test statistic is larger in magnitude or larger in absolute value than my critical value. Any questions on that? So, kind of talk about these. You got these left and these right tail tests. Now, I would not worry about flipping this sign. So this slide, maybe ignore these, right? That's true. What it's saying is true. But I think the easier way is just to always take the absolute value. And remember, you're just looking for, is your test statistic larger in magnitude or larger in absolute value than the critical value? Now, for our two-tailed test, things are going to look a little bit different. So here is where we don't know. If we have a two-tailed test, we could have evidence on the left or right side that goes against the null. So we still kind of use this method of taking the absolute value. But when we actually look up these critical values for a two-tailed test, it won't be the value that gives me alpha in the tail. It's going to be the values that give me alpha total in my tails. Well, I'm going to have the same number of standard deviations, so it goes back to almost like I'm looking at confidence intervals, where I've got half of alpha in each tail. So how do I look these critical values up? How do I find these values? Right? So right now, as we work through examples, you'll like start seeing these critical values pop up over and over again. For our right tail test, for our kind of three conventional alphas, right? 90, 95, 99% levels. We'll find the same three z values. That's because if I'm looking up an alpha of 0.01, 0.05, and 0.1 on the table, I'm always going to find the same corresponding z-score. Right? So I'm always going to find these same three values. Notice they're all positive. Now, if I had a left tail test, I'd find those exact same values, but negative. Now, for the two-tailed test, I don't look up alpha on the table, right? Because I now only have half of alpha on each tail, which is why, you know, if I want alpha in the tail to get half of alpha, my critical value is going to have to be a little bit larger, right? Or a little bit more extreme, which is why I notice that every single one of these alpha levels for a two-tailed test, the critical values we use are a little bit greater. So the way that I'll find these critical values is just like using that inverse process. So I think here I've got one. I'll skip ahead. So let's say I had a right tail test and I wanted 0.05 in that right tail. There's two ways I could look it up. I go to my Z table, actually kind of three ways. So I'm not trying to confuse you, but kind of whichever you think is the easiest, okay? So let's say we had that right tail test. And instead of 0.05 here, I had 0.1, I think I said. Was it 0.1 on the slides? No, I forget. Let's go back, make sure I'm lining up with this. Oh, no, it was 0.05. Okay, I had it right. So we have 0.05 in that right tail, and I want to find the number of standard deviations of that z value that corresponds to that. Well, I know I want 0.05 in my right tail, so if I look up just that alpha value of 0.05, oh, where's the closest to that value? Looks like I'm in between these two. So negative 1.64 and negative 1.65. So I can look up alpha to find that value, but then remember, oh, it's a right-tailed test. I want to, my kind of threshold cutoff would be 1.5 or 65 standard deviations, but positive. So I could just look up alpha and remember, oh yeah, this is a right-tailed test. It's going to be the same value since this distribution is symmetric, but positive. What I could also do is, well, if I wanted alpha in the right tail, 0.05 to the right of this critical value, what area would be to the left of that critical value? 0.05 to the right would mean that there's, here under the curve is 1, so just 0.95 to the left. So instead, if I had done it that way, if I look up 0.95 in between these two values, 1.64 and 1.65, sure enough, I found the same value, right? So I always kind of just think, I don't know, to me, it's easier to remember if it's a right-tailed test, it's just going to be positive. So just, you can look up alpha, you know, for a left-tailed test, you're going to find the negative value, so you don't have anything to do. For a right-tailed test, you'll find the correct value. It's just you're looking at the left side of the distribution, so it's the right value, but it's negative instead of positive. Now, what you could also do to kind of get the value is a little bit of a trick, which is talked a little bit about this student T table. If we go down to the very last row, we said this is kind of like our comparison row. These are the values that we would have found from the standard normal distribution. It's almost like these very specific z values are nested into our student T table for comparison. So if I wanted 0.05 in my tail, it would be this column, and then I go down to my last row, I can actually be a little bit more precise and find that the actual z value to the third decimal is 1.645. Right, with the z table, I'm kind of constrained to that second decimal, and so I kind of head to round. Okay. So all those ways are fine to find that critical value. It's just kind of whichever way you think is kind of most connects with you. Is that clear why we can use this? This isn't like grabbing a t value. Remember, this last row represents that if we ever could get a degrees of freedom of infinity, our student t becomes the standard normal. So those are going to be our standard normal values there in that last row. Okay. So let's try working through a problem. I think I've got kind of here's this is, I don't know, it's a nice visual of kind of the differences, kind of all summary slide to go back to. Right, for a right tail test, positive critical values. And kind of remember, these critical values, they just represent threshold z values. Threshold numbers of standard deviations, the way that if I see anything even further than that, I'm going to reject. So that's why here it says it's a z value, because critical values are our z values if we're looking at sample means with known population variances, or if we're looking at proportions. So right tail test, I want to find that critical value. That z value gives me alpha in the right tail. Left tail test gives me alpha in the lower left tail. Two tail gives me alpha over 2 in each tail. Okay. So let's look at this first one. So we've got our steps. I just kind of repeated that slide that I had up earlier. Let's say I want to test for whether or not more than 50%, more than 50% of the population owns a gun. All right, so I go out, I take a survey, and I find a sample portion of what, 0.41. So this one, hopefully, if we remember what we're doing with hypothesis testing, wouldn't actually be very interesting. So if I'm thinking about identifying my null alternative hypothesis here, I want to know whether or not number of people who own a gun, or sorry, the proportion of people who own a gun is greater than 0.5. But whatever I'm testing for, we said that's my alternative hypothesis. Which means my null is going to be exactly the opposite. So what type of tail test would I have here? Yeah, look at the alternative hypothesis. I've got a greater than sign. So that's going to be a greater than a right tail test. Only evidence on the right side supports the null and goes against, supports the alternative and goes against the null. So I've got this right tail test. What are my critical values going to be? Well, I'm dealing with a proportion. So I know that I'm going to be looking at that standard normal or the z tables. If I've got a right tail test, which of these so I've got 3 different critical values I want to look up. They correspond to the 1, 5, and 10% significance levels, or alphas of 0.01, 0.05, 0.1. Which of these can I rule out? The negative one for sure. Why?
It's a right tail.
Yeah, it's a right tail test. My critical values are going to be the values that give me 0.1, 0.05, and 0.01 in these right tails. And I kind of have my rejection regions. Which other ones can I rule out? The only time I have pairs of critical values is if I'm looking at a 2-tail test, right? So D doesn't make any sense because we've only got a 1-tail or a right tail test. So now we're just in between the other two. We can look all 3 of these up, and I'll kind of show you why using that student T, because that last row of the student T could save a little bit of time. So yes, we already know what these are ahead of time, but if we go to that student T table. So before I show you that, you could look at the standard normal Z table and try to find, where, what's the closest to 0.01. It's in between here, 1.2, I'm between 1.28 and 1.29. Then look up 0.05, find the corresponding Z value, then look up 0.01. Or you can remember that this last row has your Z values, or your standard normal values. Here's my column for the area of alpha of 0.01, 0.05, and 0.1. So if I scroll all the way down, 1.282, 1.645, 2.326, which if I round those kind of the second decimal would be what these values were, right? Actually, if I use that last row, I could even be a little bit more precise. I could go out to the third decimal there. Okay. Any questions on that? How I'm finding those values? Going to keep doing a lot of this, so if you're not getting it, Phil, make sure you're asking. Yeah.
So the critical values are the Z stats?
So they're going to be the Z value that corresponds to having that alpha amount in the tail. Yep. So they're not Z stats. Z stats are how far away your sample evidence is. So the thing about it is, what I'm doing with my critical values, I'm setting a threshold. Let's say it's 1.645. What I'm really saying is, if I find sample evidence that when I convert it into a Z-stat, if that sample evidence is more than 1.645 standard deviations away from what I assume to be true, then it probably isn't true. Because it shouldn't be that far away, right? Or right, I kind of know if it's that many standard deviations away, the probability of seeing it's starting to get really small. Does that help me? So in terms of getting the visual here, I could really think about this as here's my 3 critical values and the corresponding rejection regions. So now all I have to figure out is, where does my kind of test statistic fall? Now this isn't a very interesting example, but I'll give you one that's a little more interesting. So why is this one not a very interesting example? Well, let's just go back to the original values, right? What's true about my sample proportion? It's 0.41. Does that go against my null? Yeah. So if I'm assuming that the proportion is less than or equal to 0.5, did my sample evidence go against that? Well, the sample proportion was actually 0.41, so it actually supported the null. So if I found evidence supporting the null, why the hell would I reject it? We know that if we went through the steps here, we automatically are going to be failing to reject the null, and we can kind of see why these critical values with a nice, this nice visual. So we've got our critical values here. What's my test statistic going to be? Well, I drew out, yes, you don't need this for right this second. But if I think about it, right, here's my sample proportions. I was assuming that the true proportion was 0.5. I found sample evidence of 0.41. My test statistic is going to be, well, my test statistic represents the number of standard deviations away from the assumed true value I was. So that's going to be negative, right? Now from there, it's a matter of going to my formula sheet, or I guess going back to the notes if you want to, or slides, looking at that test statistic equation and plugging in that assumed true proportion of 0.5, my sample proportion of 0.41, and I think the sample size we were given was 100. Right, so I'm going to see here that I get negative 1.8, and I think I might be forgetting looking at this now. There should be a negative sign here, right? Which is why this is negative 1.8. I must have just kind of forgotten to put that in there. So 0.41 minus 0.5 gives me negative 0.09. So my test statistic is negative 1.8.
When it says Z, A, or Z off or Z by 2, that one is 2 tail times.
Yeah, so this would depend on what type of tail test we were doing. We could think about this test statistic, but would either might correspond to having half of my p-value in tail or just the entire p-value. Yeah, it's easier to not even think about that. You're just calculating the Z statistic. So I found evidence that goes against, that supported the null. It didn't go against the null. So I know I shouldn't be rejecting. Sure enough, when I plot that test statistic, if I have my critical values here, I'm nowhere near the rejection regions. So if I'm thinking about my p-value, this is going to be kind of a weird one. I've got a right tail test. My p-value would actually be the area to the right. So right away, I know which of these can't be the answer. Yeah, right. I know that this is going to have to be right. The area to the right of the mean is 0.5. I'm going to have a much larger area. I know it's going to either be B or D. How do I find what it actually is? I don't think I have it in here. So I go to my table, my Z table, look up negative 1.8. It's going to tell me the area. That's 0.03. 58. If I look that up in the Z table, I wanted the area to the right, so I then subtract that from 1. Now, once again, it's very clear to see with the critical value approach, I'm not going to reject, because I'm nowhere near the rejection region. But with a p-value of what, 0.9642, is that going to be less than any of, let me write these in order. 0.1, 0.05, 0.01. Is that going to be less than any of my kind of benchmark alphas? Not even close. So I failed to reject at every level using the p-value approach as well. Right? So kind of a unique one where we had evidence that supports the null, right? But even if we go through all the steps, we're going to see if we have evidence that supports the null, then of course we'll fail to reject it. Any questions or anything in? So the way that I was finding this 0.0358, just to kind of be clear or complete, what I should have actually done, I did this by just looking at the slide. Here we go. So if I looked up negative 1.80, I guess 0.0359, maybe I was off by 1 there. And then I would subtract that from 1 to get that 0.9642. So we already kind of said we can't reject at any of these levels, right? Given that we've got a negative test statistic, it's going to be nowhere near that rejection region, right? We have a right tail test. Now, what could be more interesting is, let's say I instead had a test statistic of positive 1.8, right? So let's, for some, instead of 0.41, we found what, 0.59. if I had a test statistic of positive 1.8, I would plot that, right? Which of the levels can I reject that with that test statistic? Well, it's in my rejection region for an alpha of 0.1. So the 10% significance level I could reject. It's in my rejection region for an alpha of 0.05. So at the 5% significance level I can reject. It's not in the rejection region for that alpha of 0.01. So I fail to reject at that 1% significance level. Or said differently, I can reject with 90 and 95% confidence, but not with 99. That might be a little bit more interesting on the test statistic there, where we can reject at some levels, but not others. Okay. Questions on that? So we can use this critical value approach, not just for proportions, right? We can use it when we don't know the population variance for a sample mean as well. So same kind of steps, right? I determine the null alternative. I figure out the alpha level and calculate my test statistic using alpha. And my degrees of freedom now, I'll find my critical value. I then compare the critical value to the test statistic to make our rejection decision. So all the principles are the same. The only difference is, well, we're looking at a sample mean now instead of a sample proportion. So our test statistic equation changes a little bit. And then when we're looking up critical values, remember, we can't use that standard normal distribution anymore. We have to use the student t distributions. Okay. So then we have to figure out what student t distribution we use. Well, it depends on our degrees of freedom. So let's work through an example like this. Okay. So let's say that I had something like this. And I want to test for whether or not the average home price in Muncie is what? Different than 90,000. So we've got an alternative hypothesis. What do we want to test for? What would I write this out as? Yeah, so that the true mean is not equal to that assumed true value of 90,000, which means we'll stack the deck against ourselves and assume the opposite is true. Okay. So I've got what type of tail test here? Two-tail. So I can think about, I've got this sample mean. I've assumed it's going to be centered around that true population, or assumed true population mean of 90,000. I then find a sample mean of 85,000, right? So what I want to do is turn that sample mean into a test statistic and plot it against my critical value. So I've got a two-tailed test. And sorry, this isn't a Z, because we only have a sample variance now. We'll be looking at a student t distribution. So for this two-tailed test, how do I find my critical values? Well, first of all, I know what they're going to be if I look at this slide right away. D, yeah, because for a two-tailed test, I could see sample evidence. That's a certain number of standard deviations to the left or the right. Now, either one of them goes against the null, right? So I can think about it. I'm going to try to find the critical value that gives me 0.1 total in my tails, which means that I'm actually going to have half of that, or 0.05 in each tail, right? And then I'm going to have critical values that correspond to having an alpha of, so here that was our 10% significance level, right? Because alpha got divided by 2, 0.1 got divided by 2 became 0.05. If I wanted the critical value for the 5% significance level, alpha is 0.05, but I've got half of alpha on each side, so corresponding to 0.025. And then here, got my last critical value for the 1% level. I kind of didn't leave myself enough room here. Let me draw this out a little bit. There we go. All right, so I've got my critical values for the 1% level. Their alpha is 0.01, so half of alpha, 0.005. So I've got these three areas that I want in my tail, 0.005, 0.025, and 0.05, right? I can look up three levels of confidence or significance at the same time, okay? So those are my three kind of alpha divided by 2 values. 0.05, 0.025, and 0.005. My degrees of freedom here, how many, I forget how many homes that I have in this sample. 51. So remember my degrees of freedom, we looked at this before, is just n minus 1. So my sample size 51 minus 1, degrees of freedom of 50. Okay. So I'll go to my student T table. Go up here. Say, okay, look. Can I get this all to be on the same slide? Not quite. So I've got the areas of 0.005, 0.025, and 0.05 that I wanted in the tail. So I'm going to be using these three columns going down to where my degrees of freedom is 50. So 1.676, 2.009, and 2.678. Right? So what did I say already? 1.676, 2.009, and 2.678. And then those same values on the other side, but negative. Right? So I've got my pairs of critical values, and I can think about for a two-tailed test, my rejection region, I've got being on either side, right? Because evidence on either side of that assumed true value can go against it now. Okay. Questions on anything there before we keep moving? About how I found those values. So I've got my rejection regions. Now it's just a matter of figuring out where does my test statistic fall relative to those. Okay. There it is. So I've got my critical values. That's kind of a truncated version of the t-table. We can get more specific out to the third decimal, the one that we looked at. So what's the test statistic? Well, first of all, my test statistic is going to have what sign? I found sample evidence that was below the assumed true value. So it should be negative. It's going to be a certain number of standard deviations below that. Now, if I'm guessing there, is it negative 3.57 or negative 0.002? Well, a test statistic of negative 0.002 would mean I found sample evidence that was 0.002 standard deviations away. I mean, 5,000, the standard deviation would have to be pretty large for me to say, mean that being 5,000 away was only 0.002 of a standard deviation. So if I'm guessing, probably 3.57, but it's really just a matter of going back to that test statistic equation. We'll have our sample mean, our sample variance, and our sample size from our sample. We'll have the hypothesized true value from our null alternative hypothesis of 90,000. It's a matter of getting those plugged in. You get this test statistic of negative 3.57. Or a different color and grab it. So where would that fall? So negative 3.57. Well, this was what? Negative 2.78, 2.009, 1.676. Negative 3.57 is like way over here, right? So this would be one where we're very clearly in the rejection region at every single level. Okay. Yeah.
So could we just take information that they give us and then plug it into that T formula right away and get the answer?
Yeah, you can do it in either order. So you can find the test statistic first, then your critical values, and then plot them. The reason why I usually do critical values first is because, like, even when I'm drawing this out, I don't really know how many standard deviations away that is yet. So, like, I don't know exactly where to plot this, right? Until I've actually turned in, well, sure enough, on this one, I find out, well, actually, the way I have this drawn is not actually correct, because that 85,000 was way out here in the tail, right? Now, I knew it was to the left. That part was okay. But in terms of like plotting it against my critical values, it usually is a little bit easier to find the critical values, draw where your rejection regions are at, and then plot the test statistic. But if you had calculated it ahead of time, then that's fine. Yeah. Any other questions on that? So one thing I wanted to point out here is what we could have also done. Instead of using the visual, like if you're like a mathematically minded person, or you just, I don't know, you don't want to waste time with the visuals and you think you can remember it anyways. I don't know, I always think visuals help, but we said if the absolute value of my critical value is less than the absolute value of my test statistic, which now we're not looking at Z statistics, we're looking at T statistics, we're coming from the student T distribution. Well, is 3.57 less than, what we have, 1.67, or sorry, greater than 1.676, 2.009, 2.678, if I'm remembering this correct. Sure enough, the absolute value of my test statistic is greater than all of those critical values, or it's greater in magnitude. Questions? So this is one where I also said on the exam, I won't ask you to find an exact p-value. Because if I wanted to use the p-value approach here, just to kind of show that they make the same, they'll make the same choice, I should be finding kind of the area that's what more extreme in my test statistic, or the area to the left of negative 3.57. Now, if I go to my student T table at that degrees of freedom of 50, the problem is the very last value is at 2.678. Now, I know the area to the left, or sorry, we're dealing with the right tail test now. The area to the right of 2.678 is, if I can get this to work, there we go, 0.005. So that means the area to the right of 3.57 would be even closer to 0, right? So this is going to be a really small p-value. But let's, for the sake of the argument, assume that the test statistic was 2.403. Well, I can find that value in the table. If my test statistic was 2.403, then the area to the right of that would be 0.01, right? Now, the T table always looks the right side of the distribution. It doesn't matter that we would have like a negative test statistic because it's symmetric. So if my test statistic was instead, oh, where would that fall? Negative 2.4, what is it, 0.03? Well, the area to the left of that is 0.01, but that's not quite my p-value because why? Remember, what kind of test do we have here? So there's one more step when I'm finding my p-value, which is I found the area in that tail. I need to multiply it by 2 because there's evidence. It was equally as likely for me to see evidence on the other side that went against the null. So here I get this p-value of 0.02. Right? Is that less than 0.1? Yes, so I reject. Is it less than 0.05? Yeah, so I reject. Is it less than 0.01? No, so I would fail to reject. Now, if instead of 3.57, I had that test statistic of 2.4, I'm using this to kind of make a point that I can't find the exact p-value from the table for this test statistic, but I could for the test statistic of 2.4. If I made the rejection decision here, my test statistic is larger than the critical value here, larger than the critical value here, not larger here. I make the exact same rejection decision. So it doesn't matter which approach I use, I'll kind of come to the same conclusion. It's just that, I'm going about it in a slightly different way. Instead of comparing the probabilities, a threshold probability to the probability of my sample evidence, I'm comparing the threshold number of standard deviations, how many standard deviations away my sample evidence was, and that is a true value. This one was starting, I don't know, kind of all come together a little bit. And we talked about a lot of these principles, like to find the critical values, we're really using that inverse process. And then to find the p-values, well, we take our test statistic to find the area of the tail. We're kind of doing that more of like just conventional process of looking up the z-value, find the course, or t-value, find the corresponding areas in the tail. So, I think I had another example here, but I might try to do a little bit of Excel today, and we can kind of come back to this. So this is, I'll put up the complete version of the slides and I'll have the answers to this one. It's just another example, some different values. I think here I probably have like a left-tailed test instead of a new phone sample pattern. Yeah, so you could do a different type of tail test. But we'll look at 3 different ones and I'll kind of draw what they look like up on the on the board. And then I'll kind of work through these Excel examples, okay, that kind of match up with those. So I put up
this HT example 2022 blank file under the in-class data folder on Canvas. Okay. So I'm saying that. Let me double check and make sure I did that. Pretty positive I did, but I'd feel like an idiot if I told you I didn't. So yep, so it's right there. Now I kind of have a completed version, but it's not going to do quite as much as we do in class. Once we work through this in class, I'll put up a version that says HT example 2022 in class work or something like that. Okay. So we got 3 different data sets here. Let's kind of start out with the one where we can, learn to walk before we can run. Okay. So this was one where I'm looking at the sample mean and I have somehow this known population variance. Okay. So I skipped some of these steps because it's really not anything that revolutionary. Hopefully it's things that are easy. So for instance, zoom in a little bit. I'm looking at this BMI variable, right? I've got this data set. Somehow it's got a couple different demographic information, but it's got BMI. So all I did was take the average or the mean of that column of data to find the mean. I was given this known population variance of 60. This would have to be given to me. This is kind of those ones where it's like, this isn't as practical. Usually we'd only have a sample variance, but sometimes we know something about the variation in the machinery. My sample size, I'm just using that count function, okay? And then over here, I wanted to do a two-tailed test, and I got a little bit lazy here. I put the coding way to sign this and then forgot to go back and check. So just to make it a little bit easier when we're looking at this, exclamation point equal sign is the coding way to say not equal to, okay? Not going to expect you to know that. That's me just being lazy and then we're not thinking about you guys not knowing that. So there's a not equal to sign in the alternative there. So I've got a two-tailed test, right? So I'm using this value of 32. Let's try to draw what we're going to be looking at here. So I've got this sample mean, and I'm assuming it's centered around 32. My sample evidence, or the sample mean I found, was 29.5 approximately. So I have a known population variance, so I can use that z-table or standard normal distribution. I can want to maybe find my test statistic, my p-value, my critical values, and make my rejection decisions. So starting out, to turn this into a test statistic, or to be more specific, a z-statistic, I'm just using that formula that I have. So I'd have to go back, find that formula if I can't remember it from scratch, kind of remember, looks something like this. Well, I've got all that information in Excel. I calculated the sample mean, I calculated I didn't calculate it. I was given the population variance. I figured out my sample size using the count function. I know that the assumed true value that I want to use, I was given that null alternative hypothesis that was using 32. It's just a matter of using Excel to be my calculator. There's no built-in formula where I can click on these things and it easily does it. Why there isn't one, I don't know. It's one doesn't exist. It hasn't been programmed into Excel. Probably because once we get down a little bit further down the road, a lot of times we can skip that step. We don't really need the test statistic if we want to find the p-values. I'm not going to kind of expect you guys to know that. By the end of the kind of hypothesis testing, we'll see that we actually could kind of skip this step. But for now, we'll just use Excel to be our calculator. So we're matching up with what we're doing in Excel, kind of how we approach this by hand. So I get this, basically just have Excel be my calculator. I don't have to type in the numbers, right? I'm just clicking on the cells where my sample mean is, my hypothesized true value is, my sample variance, my known population variance is, my sample size is. Now that I've got this test statistic, which was what, -3, I hit something. There we go, -3.89. Well, if I think about the probability that I saw sampled evidence that far away from the assumed true value, anything even further, usually that would kind of represent my p-value if this was a left-tailed test. The only problem is I've got a two-tailed test, so I can find this area in Excel, and then just remember I need to multiply it by 2. Okay. So how can I find that area in Excel? We've actually already used this formula. Nothing really new. I'm not going to show you really anything new until we get to the rejection decision today. So if I know that Z value and I want to find the area to the left of it, norm dot S dot dist. Here's that Z value, right? My test statistic here is representing a Z value. And then comma 1, just always put comma 1, always make it cumulative. We said the comma 0 has no real use for us in this class. It's always going to work just like the table does and give me the area to the left with the probability of seeing that Z value or anything below it. Now that's not quite done because we had a two-tailed test. So I still need to multiply it by 2. And I can do that all in the same cell. I can break this down into different cells. But here I get a p-value that's pretty low. Okay. Any questions on that? You want to see something again or explained again? Okay with that for now? Yeah.
When you get the information at the beginning of the question, what is like the telltale sign that like in the two-tail test, if it's
Yeah, so there I would have to be given the null and alternative, and then I see this not equal to sign in the alternative, right? Because if I have a greater than or a less than, it means that there's only evidence on one side that could go against the null. If I have a not equal to, or I'm assuming it's equal to a specific value, I could see something above that or below that, and that's inconsistent. Yep, so it's that alternative hypothesis sign that tells me if it's a two-tailed, a right-tailed, or a left-tailed test. I think I specified the alpha that we're using here is 0.05, right? So if I want to find just the critical value for that alpha of 0.05, well, now I know the area I want in the tail, right? Now I know this like threshold alpha, and I want to find the corresponding Z value or critical value, right? It kind of represents my critical value, that threshold number of standard deviations away. So I'm working in the reverse now, or the inverse. So now, instead of norm.s.dist, norm.s.inv. What area do I want in the tail? Alpha. Except it's a two-tailed test, so I actually only want half of alpha in each tail, right? So when I'm thinking here, I won't actually be looking for the critical value that gives me alpha in the tail because I should have a pair of critical values. So I've got half of alpha in each tail. Right? Now here, I can just click on alpha and divide it by 2. I don't even have to worry about kind of what that value is. Okay. So I get negative 1.96. Now, a good practice here is that it's a two-tailed test. So the problem is my critical value isn't negative 1.96. It's actually negative and positive 1.96. So in Excel, there's symbols we could insert here and then kind of to show that. Another easy way to show that is just right next to it, take the absolute value, kind of showing that there's two critical values there. Right? It might be a nice kind of easy way to do that. Okay. Any questions there before we keep moving? So at what levels can I reject the null here? Use either approach. Should be fairly easy to see. So first, I've got these critical values of negative 1.96 and 1.96. My rejection regions are kind of arrows going into the tail. I then plot my test statistic. It's pretty clearly in the rejection region there. Now, this is only one level, but I mean, negative 3.8, hopefully we're starting to realize that's pretty far away. And in fact, the numbers that we typically see, even for two-tailed tests, for our critical values that I showed you before, I think the highest one was like 2.6-ish or something. So my guess is we're going to be greater than any critical value, that we're looking at here. Now I could work out all of them here. We're just looking at the 5% significance level. And I can kind of eyeball that, or I could have looked at my p-value and said, well, my p-value is 0.001. I only reject if my p-value is less than that threshold alpha. Well, 0.0001 is less than 0.01, 0.05, and 0.1 pretty easily. So I reject it all there too. So another way you could do this to automate this in Excel, and then maybe I'll show you, I don't know. I don't know, I hesitate to use the word cool, but it shows you how you can like save a lot of time, is using an if statement, right? So this is a tool that will be useful outside of this class if you're doing work in Excel. And like I said, you know, I know that you will be using Excel, if not more than likely something more powerful than Excel, but it still uses the same principles, right? And a lot of these different programs have if statements because they're really, really useful, right? So all an if statement does is say, look, let's test to see if something's true. If it is, put this value in the cell. If it's not, put this value in the cell. So to make my rejection decision, I could do two things. I think the easiest one is if my p-value is less than alpha, comma, if that holds, well, that's when I want to reject. So put the word reject in there. Now, if you want to use text, you always have to put kind of parentheses or quotation marks around it. So that's why I kind of had to do that, because I just want to put the word in there. If you just wanted to put like the number 1 in, you just have to put 1. You don't have to put anything around numbers. It's just when you're dealing with text. Comma, if that doesn't hold, so the p-value is not less than alpha, well, then I know I should be failing to reject. Okay. So now if I hit enter, it's pretty easy to see here. My p-value is less than alpha. Hopefully I see the word reject here. Sure enough, I do. So the other way I could have done this is the critical value approach. We said if the absolute value of my critical value, oops, let me move this here, is less than the absolute value of my test statistic, we said that means, right, that I should be rejecting. If the absolute value of my test statistic is larger than the absolute value of my critical value, we should reject. So comma, if that holds, put the word reject, comma, if that doesn't hold, put the words fail to reject. Okay. So I can use either approach. Hopefully I get the same rejection decision. I hit enter. Sure enough, I do. Okay. So now the reason why, if I set this up with all these cell references, is really helpful is, first of all, I can show you a couple things, right? For one, our sample evidence wasn't that far away from that assumed true mean, but we can still reject pretty easily. Right? In fact, I might be able to even reject a value of like 31. Sure enough, I still can, right? But what gets a little bit more interesting, so let's do, I don't know, 30.5 to kind of prove this point. So now I can't reject 30.5, right? I didn't find sample evidence inconsistent enough with that I can reject the 95% confidence level. But even if I go back to 31, right, can I reject at the 95% level? Yes, but what about the 99? Well, there, if I have all my cells referenced, I can just change alpha. I can't reject at the 99% level. Right? So I get this set up. I can play around with alpha. I can play around with these different hypothesized true values. And instead of going through this process every single time, right? Every single time I'm changing my hypothesis test, all I have to do is change one value, right? All I have to do, whoops, I can test against a ton of different hypothesized true values. Okay. Questions here before we can move? Okay. I wanted to make another point here. So let's go change this back to 32 to what it originally was. And notice these rejection decisions were always mirroring each other. I was either always failing to reject from both or rejecting. So another thing I want to point out is the value of big data, right? So there's my test statistic equation. If I take really high sample sizes, am I more or less likely to be able, with the same sample evidence, like same sample mean, to be able to reject the null? So if my sample size gets really large, right, what's going to happen to the standard deviation of my sample means? Well, it's a function of my sample size, and if my sample size goes up, that standard deviation is getting smaller. So now seeing sample evidence the same distance away from that assumed true value is going to be a larger number of standard deviations away, or if I'm dividing by if I'm dividing by a smaller number, my test statistic or the number of standard deviations away I'm going to be from that assumed true value is going to be larger. Well, if my test statistic is larger, is it more or less likely that I can reject the null? Well, my critical values stay the same if my sample size changes, but if my test statistic is getting larger, it's going to be way more likely that it's in the rejection region. Right? So seeing the same sample evidence, but taking a much higher sample, let's call it like 1,000, is going to make it way more likely that I can reject, because that should make my test statistic really, really large. Sure enough, it does, right? I'm getting a p-value. So 1.8 e to the negative 24 means move the decimal point 24 places to the left. That p-value is 0. My p-value is 0, I can reject at any level, right? So it makes, and also notice now I can actually probably reject, maybe not 30, but probably pretty close, 30.1, 30.2, right? So even seeing something not even one whole BMI value away, I can still reject that, right? But it's because I had a big sample size. Now, I can't just change my sample size in Excel, right? But like I'd actually have to go out and gather more data. But I was just kind of playing around with that to kind of show you why having those larger sample sizes is nice. Okay. Any questions there before we keep moving? All right. So the other one I want to show you, and I'll skip this proportion one for now. Might come back to it on Wednesday. It's not that much different. It's the same functions, right? The test statistic equation looks a little bit different, but to find the p-value, to find the critical value, we're still using norm.s.dist, norm.s.inv, and then we can do the rejection decision using the if statement again. So let's look at one. I know what this is. So this is, I don't know. I found some data about what they called e-cigarette use, but basically kids vaping. And this was like, I took out some of the variables. So I think here we're going to look at, so these were all the kids who had ever used, and they were all like middle school, elementary school. And then they had the age they first kind of tried to vape, right? So I found the sample mean of that age, just using that average function, sample size, using that count function, sample variance, using that var.s. This is all stuff that we've already done, right? Now to calculate my test statistic, it's exactly the same as what we had before. It's just now I'm only using a sample variance, so I have to use that student t-distribution. So I got that test. Oops, sorry. Go over here. Here's my hypothesized true value. Let's change this to 14, right? That's what I wanted it to be. So my test statistic, I just take that sample mean minus the assumed true mean, then divide it by the square root of my sample size, sample variance over my sample size. That's just using Excel to be my calculator for my test statistic. Like I said, I wish there was a built-in function for it, but there's not, okay? Now to find my p-value, here I've got a left-tailed test, okay? So I've got this test statistic of negative 9.45. I want the area to the left of it. I can't use the norm.s.dist, but there is if I can type, a t.dist, right? I'm using the student t-distribution. I want the area to the left of this test statistic, this t-value. So put my equal sign here. Tell it that t-value, right, or your test statistic, then comma, well, what's my degrees of freedom? My sample size minus 1. And then just like we were doing before, comma 1 gives me that area to the left. Okay. Yeah.
Is there a scenario where degrees of freedom isn't minus 1? So it doesn't automatically do that, even though?
No. So this, yeah, interesting that they don't have it built in. So in the t.dist, you're telling it which student t-distribution you're using. So you're telling it your degrees of freedom. I agree with you. They could automate it a little bit more, right? Seems like it'd be pretty easy to program in there. In fact, some of the later stuff we use actually has it programmed in there. I think the reason why it's not here, let me think if I can think of why they might not have wanted that.
I don't know if it's just like,
I think it's more of like technical, like you're supposed to be using the degrees of freedom from the mathematical, like that lines up with a mathematical proof. So that's probably why they want that as the data entry there. But you're right. Like I could just program it to tell it the sample size and then subtract one.
So there's no scenario ever where degrees of freedom is.
Anything other than n-1. For what we're doing, when we get to some two population stuff, the degrees of freedom becomes a little bit trickier. So that's also maybe why it doesn't just automatically subtract from one, because if you're not applying to this specific case and you're doing two population stuff, you may actually not want it to automatically do that. Okay. So here, pretty big test statistic. So our p-value is really small again, right? Not that interesting. I mean, we got a huge sample size. Okay. If we wanted to instead find the critical value, instead of using norm.s.inv and then telling it kind of the area we want in the tail, well, now it's t.inv. Well, I've got an alpha of 0.1 here. I've got a left-tailed test, so that's the area of my left tail, so I don't have to worry about dividing it by 2 because it's not a two-tailed test, subtracting from 1 because it's not a right tail, comma, here's my degrees of freedom, sample size -1. Now I've got my critical value. Now notice, this looks pretty close to what we would find from the normal distribution, but that's because my sample size is really large, right? So when my sample size is getting closer and closer to infinity, those t-values become really close to the z-values. Okay. And then from here, it's just like what we did before. I can use my if statements. If the p-value is less than alpha, comma, put the word reject. If it's not, put the words fail to reject. Okay. Then I could do the same thing with the critical value approach, comparing the absolute value of my test statistic to the absolute value of my critical value would look no different than what we did before, right? So the only real difference here is when we only had a sample variance, we had to use the t.dist and then the t.inv. Okay. Any questions or want to see one of those cells again? So point out a couple things here. Notice I can reject at the 90% level that the true average age that someone first tries an e-cigarette or a vape here. I found sample evidence that wasn't even that inconsistent with that assumed true value, right? It's just barely below 14. But because my sample size is so large, right, that's actually going to represent a high number of standard deviations. In fact, almost 9.5, right? So having high sample sizes makes it pretty easy to reject values that are inconsistent with what you saw from your sample. And it intuitively makes sense. If my sample is larger, I have a larger proportion of the population. It should be more informative about what the true population value actually is. Okay. Also, just to point out, this is like this is wild to me that there's like 8 years old was the first age here. I don't know how that happens, but there's a couple of them in the data set. So, but you can play around with this value. Like how close can I get? What about 13.9? Okay, I can still reject that. 13.7. Okay, I can't, I failed to reject that. Maybe 13.75. Oh, I actually still reject that one as well. So you can play around real quick with different hypothesized true values if you've got it set up this way. Okay. Okay. So I think I want to show you one more thing before we leave, just to kind of prove to you this isn't completely false. Okay. So I had this other file, and I wouldn't push you guys this far, but I think I showed you one similar for the confidence intervals. But I think it kind of helps give a good understanding. So I went out and grabbed a bunch of different major universities, and I think I had an older time, 2012, so a little bit older. But they put out their tuition amounts, right? So across these universities, and they varied a lot in size, but I found kind of the true population mean, right? I found the true population variance, right? And so I kind of cheated. I knew what the population mean and the population variance were. I then took a bunch of random samples. So, you can kind of see here, there's a random number generator. I then use this VLOOKUP thing, which is really cool, but we don't have time to go through in this class. I highly suggest, if you want to get more proficient in Excel, just search VLOOKUP on YouTube. There's tons of tutorials. Very, very useful. So it looks up these different student IDs, or sorry, college IDs, and puts their tuition amount in there. I then did that for a bunch of different samples, right? So I took a whole bunch of random samples, and I think they're all of size 50. Yeah, 50 to 1,000 samples. I then came down here and said, okay, look, from this sample, if I use this sample's sample mean, it's sample variance, and then I know the sample size, each sample is size 50. Well, I've got that assumed true mean, right? So I can kind of come up here. Oh, where did I put that? I think it's over here somewhere. Right. So I said, I'm going to assume that the true mean is 13,055, right? Which is actually what the true population mean was. So I shouldn't be finding samples where I can reject this unless it gets past that threshold alpha, right? So I come down here, I calculate my test statistic for that sample. I then use, I'm doing a two-tailed test here. So I use that norm.s.dist, find the area of my tail, multiply it by 2, figure out what my p-value is. Now notice for my p-values, for some of them, it's really large because I found sample evidence that was really close to that assumed true value. Right? So remember here, my assumed true value, I could cheat, so I knew it was the correct value. Here I just said, look, if that p-value is less than alpha, put a 1. That means I should reject. If it's not, put a 0. That represents I failed to reject. So for each one of these samples, I made that rejection decision. So if what I assume to be true is in fact true, then across these 1,000 samples, I'll be making type 1 errors, whatever I set alpha to be. So when I was comparing the p-value to alpha here, I believe I had alpha set to be 0.1. So of these 1,000 samples, I should be seeing what, 900 zeros and 100 ones, right? I should be rejecting 100 times or 10% of the time, even though I shouldn't have been, because I could cheat. I assumed the correct value here, so I could kind of cheat on this one. Sure enough, the number of rejections I see is right around 100. Now, it's not precise because I only have 1,000 samples. If I took like 10,000, it'd be even closer, right? And kind of with that random number generator, every time I hit enter here, I go into a cell, it generates new random numbers. So notice this is kind of always, whoops, living right around 100. It's not like exactly 100 every single time, but I don't know. This kind of, I think, helps kind of prove the point of like, my hypothesis test will be right, even if what I'm assuming to be true is in fact true. I'll only be rejecting when I shouldn't be, whatever I set alpha to be. Right? In fact, here, I can change that by going up here, because I think I had alpha, hopefully, in a cell. Now, let's say I change alpha to 0.01. Well, now I should only be getting 10 out of the 1,000. So I'll hit enter, come down here. Oops. Sure enough. Oh, this one was pretty low, 4. I just got us around 13, 13, 12. Right, it's going to float right around 10 there. So I don't know. I always kind of like proving something to myself with data as opposed to going through mathematical proof. We'll do a little more Excel. I'm going to introduce 2 population examples on Wednesday. We're going to do some more hypothesis testing. We'll do hypothesis testing for 2 populations on Monday of the week of Thanksgiving. And then once we come back, we won't have a lot more hypothesis testing to do. We'll actually jump to linear regression. So if you want your exam on the way out, I have all of them. Feel free to kind of get them on the way out. Okay. See you guys on Wednesday. Let me stop.